Even though there are around 6,000 known minerals, 90% of rocks are made up of just these seven minerals. So these are the only ones we're going to look at because they're the only ones you're really going to see when you're looking at rocks. So as you can see here, the ones that are less dense are the feldspars and the quartz, and they make up the majority of the Earth's crust. But actually, on the surface of the crust is what you will only see really, and so the majority of what you're going to see is quartz, and that's because the lighter ones float up to the top of the Earth, and they cool down and form the crust, and the heavier elements sink. So another thing you're going to notice is that these are all igneous formations, so they are crystallization of the magma or lava. Um, and the seventh one that's not included in that particular list is calcite, and it forms by precipitation of biological processes. The other thing to be aware of is they sometimes they include other versions. So feldspar can be plagioclase or orthoclase. Mica can be muscovite or biotite. One's white, one's black. And some of them go by different names like hornbende or augite. Now, another thing you can note from the chemical composition of these minerals is that the quartz and the feldspar have also the silicon, oxygen, calcium, aluminium, silicon are lighter than these denser ones that have things like iron and magnesium, well, especially iron in them. There's also just an overview of the key features, but we're going to go into each one in detail. So, first of all, why do we have these different minerals? How do we know what these minerals are and how they form? They come from this guy called Bowen, and what he did was he melted magma, which melts at about 1,300, and then he stopped it and cooled it at different temperatures and examined which rocks were formed. And so he found that the first ones to cool were olivine, then pyroxene, then amphibole, then biotite, and then finally the feldspars, the micas, and the quartzes. And so the feldspars here are just a continuous change as it heats up. And why is this significant? Well, you would think that the first one to start crystallizing would give the largest crystals. But as I said before, these things actually form crystals and they're more dense. And so, as you can see from this diagram here, they first form crystals, but because they're more dense, they go down and they sink, and then they remelt. As whereas the cooler magma is more viscous and more dense, and then the lighter quartz and feldspars, so they're not as dense and they'll float, and also it's more viscous. So they're the ones that actually form the crystals because they don't remelt, they don't sink and remelt. All right, so that diagram probably a little bit confusing. And what is the point of that? Well, the point is you're only going to get these crystals are quite rare because they just remelt and sink um, when they form early, and these later crystals they don't sink and they stay there and they have time to form without being dissolved or used up. And so when you get an eruption, that's when you're likely to get some of these crystals, although it's hard to find them. So that's the point. The olivine and the pyroxene, I don't really have samples because they are difficult to find. They just do remelt and don't form large crystals. I've only got a picture of a pyroxene crystal. It should look like this. It should be black and have 90-degree cleavages, slightly off 90, and we'll talk about that with some actual pictures. So I do have a rock here that contains olivine or other types of crystals. Rocks don't have cleavage points, and only minerals do. Well, some don't. And olivine's one of those that doesn't have a cleavage point. So you can't see faces reflecting. And so I'm not sure if this is actually an olivine mineral or if olivine rock. Because if it was a rock, it would have no cleavage faces either. So planes in the crystal that break in weak points. So if it's something green, it's most likely olivine, says the quite a good geology professor, Sean Wisely is his name, who gives very good lectures on all these things. And I've got a lot of information off him plus other sources. What I have here is probably a mixture of different olivine materials. You can see from this picture here That's why it looks very similar to what I have if you look at the microscope picture compared to this picture. So I think I've got a mixture of olivine minerals and I've got a rock. Other than that, you can see that the substance, it does scratch glass, it has a non-metallic luster, and it has no cleavage planes. Well, because it's a rock and it's not the mineral. And it is green. Okay, so it's almost definitely olivine mineral, or most likely a rock high in olivine crystals. The next one we're going on to is quartz. And so this sample rock helps us with the analysis of olivine and the sort of mixture that you can see. So here we have a mineral close to quartz, which is smoky quartz, which is basically the brown caused by small amounts of aluminium added to a quartz crystal. So it's pretty much a quartz crystal with a little bit of aluminium in it. It works its way down to what looks like pure quartz, or probably possibly a mixture of minerals, which would then be quartzite. And then the grey area on the outside is the quartz crystals. It looks just like granite. You can see at the start. And if you compare it to granite, you can see the pink and white at the feldspar crystals, the black crystals, and the mica. And so you can see that even a rock can transition into a mineral and vice versa. So that just be aware of the complexities of this mineral rock um, dichotomy. Quartz also has a complexity that can be various forms. So you can have this weathered looking rock, which could be quartz. It's a polished up one. It's had all its edges polished up. You can see at the bottom as well. The real crystal here, or a mesh of interlocking crystals. And so going from the tables now, we can see that it does scratch glass, and it is a six-sided crystal with no cleavage planes. It has conchoidal fracturing, which is a curved fracture like you see in glass, and this is easy to confuse with marble, which is not a clear crystal you can see here. When it's not a clear crystal, it can be confused with marble. So I did actually break one up here and see if it reacted with acid. Marble is made of calcite mineral and it will react with acid, and this one did not. The next one is feldspar. This is given other names such as orthoclase or plagioclase when it is in different percentages of elements, potassium, sodium, or calcium, to give slightly different colors of pink, white, and grey. You can see the cleavage planes only in crystals and not in the rocks. And so this one has cleavage planes, so it must be the crystal and it's not a rock. The reflection of light shows you where the crystal breaks off in its plane, and this occurs at 90-degree angles. So just to confirm it with the table, it also scratches glass and has a non-metallic luster. Next one is mica. Biotite is the black form, muscovite is the clear form. It has a non-metallic luster. It can't scratch glass, but it can scratch my fingernail. Just, I think. All right, you can see two cleavage points. A thicker example shows no reflections on the ends, and you can see flexible shields can be peeled, which is quite unique. The next one is Amphibole, which is common name is also old name is hornblende. Again, just to check, see it scratches glass, has a non-metallic luster. For comparison, a metallic luster, because it almost looks metallic, looks like a metal such as this pyrite or the stibtite, and you can see long black shiny crystals. The cleavage planes are also quite distinctive for this. You can see it's at 60 degrees and 100-degree angles. And the last one is calcite, the only non-igneous mineral. Softer than glass, you can see, but does scratch your fingernail. It has three cleavage points, a rhombohedral shaped crystal, and it also, just confirming here, it does also react with acid. Okay, so hopefully you can use those tables. The main issue is getting a good sample of the mineral to be able to confirm. Once you have a good sample of the mineral, using those tables makes it quite easy to work out which mineral it is. And those minerals make up pretty much all the rocks, all right? The other 6,000 or so minerals make up the other 10% of rocks.